Okay, so in this video we are going to look at what S25 is. Of course, I have pre-written the actual flow chart of how it's going to look like. So before that, I just want to look at some things which actually motivated me to come up with such a protocol. So the first thing is when we look at cryptography, when we look at something like RSA or AES protocol or some other existing ones. So we have, let me just try. So of course RSA is going to be blown apart by Shor's factoring, and of course there's another theorem which is called as Chinese remainder theorem, which actually kind of combines with the factoring algorithm. So what RSA does is it takes two large primes and then it multiplies them together and then it creates some kind of a code based on this. And to crack the code, you need to factor out the huge number into these primes, which is not actually trivial. So what classically what we can do is we can take uh, so let's say this is equal to some k. K stands for key. So we what we do is we look at first square root of k numbers, and then we can check whether it's a factor or not. So this is what the classic part actually is. But Shor's factoring uses this neat little algebraic trick where it looks at um, something like k to the so k to something mod g, and then it kind of uh, looks at it. So what the actual order? So this is of course the order of course. So this is O of 10 to the power half, and then for quantum, of course it is uh, order of log n whole cube. This is quite a bit of improvement, and yes. To be honest, when we look at RSA and things which are like RSA, for example, P versus NP problem, we come across this kind of inconsistency in the fact that if I have a strong enough computer, I can do this. If I have a strong enough system where I can actually look at all of these numbers simultaneously, multiple times in a second, I can crack this before the message even goes to the receiver, which means that the entire thing is completely broken apart. Okay, so there are a few more types of things which I would like to look upon. So I mean, the history of cryptography, it began, I think, very early. They used to just, like just scramble the numbers or scramble the alphabets in this thing. So there are multiple kinds of attacks that we can do. So if it's a static encryption, so we can, if it is in some language, so let's say English, French, or something, we can use something called as a zip attack. So what this actually is it comes from the Zipf's empirical statement, which says that if I have uh, so the frequency or probability of some letter, so let's say some character C1 is going to be directly proportional to 1 over um, uh, sorry, P of Ci is going to be 1 over I. So what this actually tells me, so let's just look a little bit into this. So I'm considering the arrangement C1, C2, C3 and so on. based on which of them are the most likely. So I'm going to pick up a huge book like Romeo and Juliet or Hamlet or some other book, and then I'm going to start tallying up all of the characters. So what I'm going to usually get if I ignore spaces is that I'm going to get E as character 1 and then A as character 2 and so on. So now what the actual statement says is the probability of getting this character or whatever character it is proportional to 1 over I. So which means this is 1. So E is going to be 1, A is going to be half, and then C3 is going to be 1 over 3 and so on. So this was an empirical proof, empirical statement, but we do have certain proofs. For example, if we do look at English literature, we do find that it follows, the frequency actually follows this sort of a rule. So now with static encryptions, what I can do is I can look at some character, and if it appears with, let's say, 1, with the probability proportional to 1, then I can say that it is going to be equal to E. And if it is exactly half of that, then I can say it is A. So, okay, so let me just demonstrate. So if I have a text here, and then the letter K appears most frequently, and L appears half the time. So then K can be mapped to E and L can be mapped to A, and the encryption is broken. So this is the zip attack. And of course, we did discuss the number splitting and how BB84 and everything works upon. So now one more thing which I want to discuss is something called as zero knowledge proofs. So let us look at this particular scenario. So let's say A wants to know if B took some course in a particular university. Of course, let's assume that this course is going to be offered by only one professor throughout history. Let's say it's a very new college, and then the professor has some kind of a characteristic, or maybe they look at students in a particular way. For example, they look at only left to right or right to left, so maybe right to middle, or some sort of a combination of those, or probably he repeats a lot of words he says, or maybe he or she scratches their head whenever they. So some character like that. So so A is the verifier and B is the person is being verified. So I'll just call him answerer. So what B says to A is, hey man, I don't want to show any credentials of me finishing the course, but I want to convince you that I took this course, and by taking this course, I know that professor does this particular thing, or let's say he walks left to right every time he mentions the questions to students, even though everything is written on the everything is written everywhere on the board, or maybe he does something like that. So by describing something which does not have any direct correlation to the actual question, but which is a critical part of answering the question, B can effectively communicate to A that he has solved the problem or done the course or whatever it is without actually giving out all of the information. So if C, another person, sees this, he's going to assume that they're just having a weird conversation of some sort. And then, but what he doesn't know is that because A and B have both taken, both solved that problem, they know of information which C might not know. So, what does that look like in terms of S25? So, the original idea was that A and B are speaking. So, A goes first. Let's just put a dash here. He says some statement. Let's say K1. So, this could be any sort of statement. So, one which I was looking at is let's say pizzas are round, or earth is flat, or some arbitrary sentence which has a correct grammatical meaning. So the correct grammatical meaning is plays a very important role, and I'm going to be getting to that in uh, the actual flowchart and the actual steps. So he says some K1, again completely unrelated to the fact, and then B looks at it and he says some K2. Or A can also say some K2, it could be anything, but usually it is like back and forth, a conversation happens back and forth. So then K3, and both of them can agree upon some code. Okay. So now this is the actual thought process of that. And when we look at something in English, so let's say A says, so let's say A says I like strawberries, B says earth is round, and A again says black clouds are square, and B says curtains are pizza. This looks this looks like it doesn't make any sense. But what internally is happening is they are exchanging some sort of a code in clear language. And then if you take A and B both separately, they both would say that, okay, fine, I communicated with the other person and the code is 15112130. So this actually does not make any sense if you look at it from an attacker point of view. But in order to actually understand how and what S25 is capable of doing, we go over a lot of assumptions, maybe in MMI minus one, or even something like an omniscient attacker. Uh, so yeah, that is the way that I envision S25 to actually work. Uh, okay, so let us look at what exactly is happening in the protocol. So I'm going to be writing the steps. So the very first step is I'm going to create multiple files called K superscript n. So these are random files, they contain random zeros and ones, or you can even do it with a particular set. So the set could be 0, 1, 2, 3, or 1, 2, 3, 4, or any such set. And then I'm going to choose a particular file. So, okay, so one, and so this is the picture. So I have all of my keys here, and I'm going to choose one of them. So let's say I choose this particular one, and I enlarge it. So the second step is I choose a snippet uh, and call it K1. Okay, so what this looks like here is I'm going to start somewhere and I'm going to end somewhere. I'm going to choose this as my K1. Okay, so the third step is, now comes the interesting part. We can either go, if you have a really powerful computer and if we do not care about this case, you can actually do the alarm right now. But Uh, I prefer to not do it in this particular step because it leads to so many other issues, mainly in these attacking spaces and stuff. So what I'm going to do is I'm just going to put the quantum aspect right at number 3. So what this quantum aspect is, I'm going to come a bit later on. So what I'm going to do is, in this I'm going to generate n1 number of beta xx. So this beta xx, so beta 00 is equal to 00 plus 11 over square root of 2. Beta 01 is going to be 01, so 00 minus 11 over square root of 2. Then beta 10 is going to be 00 plus, sorry, so 01 plus 10 over square root of 2, and then beta 11 is going to be equal to 01 minus 10 over square root of 2. So I'm going to be picking n1 number of qubits with either of these configurations. Then what I'm going to do is I'm going to do the if I'm let's put it as the next step. So what I'm going to do in this case is I'm going to quantum teleport this. The next step is I do the error correction codes. I'm just going to represent it ECC, and I apply something called as correction gates. Oh, sorry, I'm going to teleport to B, plus I'm going to include the bases. Again, the basis is also randomized. Okay, so we have the actual basis, and then we do have the beta axis. So now, when we include the basis, we are eliminating the need for these lossy qubits. For example, in BV84, when the bases do not match, we discard that particular bit. But once I include bases, we don't need to actually discard those bits. And then I'm going to apply something called as correction gates. So now, what are these correction gates? So let us look at what A measures. So when we are teleporting and A measures, let's say measures the final psi, uh, what does A get? So let's say A can get either 0 or 1, and B can get either 0 or 1. So again, if it is 0, 0, 0, then it can be either beta, I mean the corresponding beta states. So now, what I'm going to look at is, I'm going to look at my snippet K1. So this can be either I or X. Same thing. So this actually depends on K1. So let me explain further by taking one particular case. So let's say I take this 0, 0 plus 1, 1 over square root of 2, and let's say A measures either 0 or 1. B also measures either 0 or 1. Now, if the snippet K, K1, corresponding to this qubit is, let's say, 0. If A has gotten 0, then B has also gotten 0. So which means there's I to be applied here. If k1 is equal to 0 and both of them, I mean, if A has gotten 1, A sends that he has applied an X gate here. These two are not possible because this is the other basis. Um, yeah, but because A knows what exactly the basis is and what beta state I'm looking at, he can infer which gate he has actually put into the actual to match K1 and the whatever code he's being sent. So this is in that case. So if we look at 0 1 plus 1 0, uh, the exact same thing. So if A measures 0, then B measures 1. So if K1 is equal to 0, if A measures 0, then he has to send an X gate. I mean, like he has applied the X gate. So the X can be either a 0 or a 1. So 0 indicating that nothing has been applied, and 1 being X has been applied. Again, so if A measures 1, then we know that B has measured 0. Then we can send an I gate or 0. So these are the correction gates. So let me represent them in a proper way. So, 0, so beta 1x. So beta 1x means x can be either 1 or 0. So we know that it is 0, 1 and 1, 0. So what I'm going to write is A, B, k equal to 1, 1, 0. So this is going to be the actual thing. So A, 1, 0, B, 1, 0. And of course I'm going to write the k1 here as a set of this. One being either in what to do if k is equal to 1 and what to do if k equal to 0. So if you have 1x, only these two are going to survive. So here what is going to happen is if I have 1 and if a measures 0, then I know that b is measuring 1. So I apply an x gate, and if it is 0, then I apply an I gate. So similarly, if I measure 1 and k is equal to 1, then we know b has measured 0. Then again I have to put an x and I gate. So for beta 0x, I know that A has measured 1, B also has measured 1, so I have to put in I gate here. And similarly for the last one. So the purpose of these correction gates is to make it so that the code which I am sending it to the receiver matches my snippet. So why am I doing this? It will become much more clearer, because if I have a random code, I cannot directly pick at what K1 is going to be after the state reductions. So we'll go into that a little bit later on. So now after this, both A and B create something called as states. So what exactly these states are is that they store the position or the. Of course, this file is going to be so huge that there are going to be multiple such K1 occurrences. And then what they say is, they create these kind of dots here. So what these dots represent is at that point, I have the snippet K1 appearing. So that is what the states mean. The state means that what is the actual position that K1 has appeared. Okay, so let's move on to the next one. Now, so this is a process where A or B can transmit data. For simplistic case, we just assume A is the person who's creating and sending everything. So now, what A does is going to do the exact same thing. He's going to choose a snippet. Now, what he does is he chooses a language. So So he chooses a snippet and he chooses some arbitrary language. It can be any of them. It can be even a mathematically defined one. And then he looks at the snippet and he looks at the language and sees which of these languages have the closest distance. So, for example, if that language has bits, okay, so um, if I were to look at K1 and change the least amount of bits so that it forms a sentence in this language, I'm going to put that particular sentence in. I'm not going to be directly sending the snippet. I'm going to be sending the language or the sentence which is closest to the snippet. And then I'm going to be sending it. So 3, 4, 5. So again, I'm going to be using this kind of block to be sending this language sentence to be, and of course, I'm going to be applying the error correction gates, error correction code, and the correction gates, so that the receiver has a particular language. So when we discussed about what S25 actually would look like in the first part of this, I did say that we are going to be using this kind of arbitrary sentences. So again, this language sentence is going to be one of those arbitrary sentences. It can make sense, it cannot make sense, but it has to be grammatically correct. So again, we will discuss what exactly this means when we look at the language recognition module, or LRM encoding, LRM decoding. And then we are going to then both A and B reduce states. So there's an issue with A, so that he actually knows what the snippet is. So we cannot just pick whatever snippet he has, and we cannot just look at all of the things which are the closest. So what A does is A looks at only A kind of deletes this from his memory, deletes K1, and then looks at only the K2. So this is the snippet K2, and then he looks at only the language which he has sent. So using that common thing, they both reduce their states. So which means both of them now share the same state. And of course the frequency is going to decrease very much. And then they're going to, so essentially what A does is, he looks at the language sentence, and then he sees which of them, which of the particular KIs or which of the particular states is having this particular language closest. So that's a lot to unpack. So let me clarify it further. So A now has language. So the language, I'm going to call it N, N1. Oh, sorry, N. Yeah, so N2, because N1 is A1. So A has N2, and now what A does is he takes these K, whatever these instances that he has, whatever states that he has, and then he checks which of these have the closest LRM or the closest language sentence as N2. So he takes this K2 and then he checks the distance. So this is the Manhattan distance, or some other sort of distance metric. So K2 checks the distance of, A checks the distance of K2 to all of these ends, and whichever ends have, whichever K2 instances have N2 as the closest, he's going to reduce the states based on that. So now, because B also has the same exact information, he also reduces to the common shared state. So this goes on until we have a unique key. So that means that upon sending the particular kn, there is only one possible state that both A and B can agree upon. Okay, so now that we have the unique key state, what we are going to do is we are going to apply a transformation. This is the final transformation for master key. So I'm going to having K1, K2, K3 and so on and so on. If I look at the particular state, just before these values, I'm going to be getting K1, K2, K3 and so on. Of course, when we're actually demonstrating it, I can show exactly what is happening. But what exactly is the thing happening here is that we are kind of going back and forth trying to agree upon a particular um, geographic point on the uh, final file. So after that, what we do is we generally avoid this k1 to kn, and then we pick something else, some other transformation. For example, so let's say that we have k1, k2, k3, kn. So my code starts from kn plus 1. So just after the final key, or the just after the final state. So that is how I'm going to be getting my master key. Of course, this can be different. So I can say you have that position number as something like 1500. Add 2 to it, and then your code starts. Or you can have multiplied by 2, or you can say every second one. So it's going to be 1500 1502, and so on. Of course, this is uh, left for both of them to decide what exactly it is. So of course, this is just the gist of it, and this is how it's going to look like. So I'm going to be generating the file, choosing the snippet, doing the quantum aspect, the 345, and then I'm going to begin a cascading sequence. So this cascading sequence is this repetition until I get a unique key state. So I'm going to choose the nth message, then I'm going to do LRM encoding, which is the nearest language, and then I'm going to do the quantum aspect 345. Then I'm going to do LRM decoding, and then finally I'm going to do state reduction based on the message sent. Okay, so I think this is the time where I have to tell what LRM actually stands for. Uh, So it is a language redefinition module, and of course we are going to look at what exactly LRM is, and then we also look at why we need such a module, and why can't we use the existing languages. Uh, and then there is also going to be some kind of AI when I'm. So of course, let's just write it down. So this language redefinition module is going to be using some sort of an artificial intelligence, uh, basically in the form of NLP. So NLP stands for Natural Language Processing. It uses something called as a recursive neural network to actually train. We are going to be discussing that a little bit on that as well. So again, we can use a classical AI, we can use a quantum AI as well in this case. Um, So the quantum AI, the way I envision it is that it can do all of the things that classical AI can do, but it uses quantum storage or quantum algorithms to run. So that is the introduction to S25 and all of its basic steps. So next we'll go into actual um, the explanation of all of them. Oh, before we go, there is one more section which I want to introduce. and that is what happens if I have qubits. So these are information entities which have 0, 1, and 2. So in this case, what I can do is the Hadamard, if I define Hadamard as 0, 1, then the Hadamard gate is going to be applied on this particular thing. And if it is, let's say, 1, 2, then it's going to be applied on this particular thing. And then this adds another security layer to my actual qubit. So every time I have a different basis and the attacker measures it in a different basis, the qubit is actually invalidated, which means that there is no information that the receiver can extract from the qubit. So this also provides a separate layer, and of course all of the performance metrics, all of the security metrics, everything is going to change. So what I'm talking about is, let's say I have this qubit 0, so qubit. Qubit. So I have 0, and now I apply Hadamard gate, which is consists of zeros and ones. 0, 1. So this is going to be 0 plus 1 whole square root of 2. But if I apply hex 0, 2, then I'm going to get 0 plus 2 whole square root of 2. If I measure this in 0, in this kind of plus 0, 1 state, then I'm not going to be getting the exact value. And similarly, if I measure it in some different basis, I'm not going to be getting the exact same value. So qubits and higher informational entities can be used to increase the security, but we do have a practical constraint. So right now, qubits are not exactly stable as of 2025. And qubits are very, very unstable, and we probably cannot transfer them over a communication channel, especially with all of the noise injections and natural decoherence, etc. That can be a physical constraint from the laser's perspective, or even the actual, you know, trapping the qubit and then actually performing the measurements in particular basis. So everything becomes extremely complicated. And with qubits, we cannot really use lasers because it has only two axes for polarization. Maybe we have to use something like a hydrogen atom in a particular state. So let's say H in state, let's say 200, sorry, 210, 1 minus 1, and then 211. So this is actually in hydrogen atom. When we look at the energy states, we have N, L, Ml. N, L, Ml. So N is the quantum of the energy. So what actually is the energy of the hydrogen atom? L is going to be the angular momentum in the quanta of angular momentum. So it can be 0, 1, or till n. And then ml is going to be the z projection of the L. So we can use hydrogen states, and of course, in quantum mechanics itself, we do encounter this kind of a gate where we represent these things as part of zero plus or minus basis. This is used when they regenerate and we are not able to really work with them. So that's it for this video.